In this video, for the t-test for two independent samples, we're going to talk about the assumptions we make when we're doing the test, and then go through the Fmax test calculations. So again, when we do a statistical analysis, we're always making some sort of assumption. And it might change a little bit depending on the type of statistical analysis. So for an independent measures t-test, one assumption we make is that the observations within each sample are independent. We have two separate samples, and the observations we make in one sample are completely separate and independent of the observations we make in the other sample. The two populations must be normal, so that the populations from which we're taking those samples have a normal distribution. We're also making the assumption that the two populations must have equal variances, so that the variance in population 1 and the sample 1 is equal to the variance in population 2 and the sample 2. And this is called homogeneity of variance. And you'll see this when you do SPSS analysis. It will automatically calculate that for you. So what we're going to talk about now is how do you know if that homogeneity of variance assumption is satisfied? And that's something called the Hartley's Fmax test. So the test for homogeneity of variance is this Fmax test, where we take the variance, the largest variance between the two samples, over the smallest variance. And so it's just a simple fraction. And then again, just to remind ourselves, variance is that sum of squared deviations over degrees of freedom. So a large value indicates a large difference between sample variances, which is what we don't want. A small value near 1 indicates similar sample variances, and that is what we do want. So we're already very familiar with this formula to calculate variance. Now we need that in order to calculate our Fmax, which is going to test that homogeneity of variance. So in this example, for a sample of n equals 7 participants with 2 or fewer negative experiences, the average well-being score is a mean of 41 with a variance of 50. And for another sample with a mean of 7 participants with 5 to 10 negative experiences, the average score is 48 with a variance of 62. So to calculate the Fmax, we're going to look at these two variances. 62 is the largest sample variance, so we take that and we put it over 50. And that gives us an Fmax ratio of 1.24. So now what we need to do is compare the computed Fmax ratio. So computed Fmax was 1.24. We need to compare that to a critical value. So in order to get the critical value, we need a few things. We need to know the number of separate samples. In this study, we have 2 samples. We also need to know the degrees of freedom. So the Hartley Fmax test assumes that the degrees of freedom, or the n, the sample size, is the same for both samples. So in this sample, in this test example, both of our samples did have the same size. N was equal to 7. So our degrees of freedom, 7 minus 1, or 6. We also need to know our alpha level. So our alpha level was 0.05. And the goal here is to not reject the null hypothesis. We want to fail to reject the null hypothesis because we want that Fmax to be the same. We want those two variances to be the same. So again, going back to our example, we said this was 2, this was 6, and this was 0.05. So we have to go to a table to find the critical Fmax value. Now here, critical values for 0.05 are in light face type, so they're the ones that aren't in bold. And for 0.01, they are in boldface. So we said 0.05. So we had the number of samples. So for an independent measures, it's 2. N minus 1 was 6. And we're here then in this 0.05 region. At 5.82. So if our Fmax value that we calculated is 1.24, and our critical value is 5.82, our calculated value is well within the expected region, nice and close to 1, so that suggests that our two sample sizes comply with that assumption of homogeneity of